All right, so what have we seen today? So we saw a lot of recent progress on the front of on the optimization front and the learning front around min-max optimization. We saw an application of min-max in reinforcement learning. And for our last talk today, it's a pleasure to introduce Nathan Kallus from Cornell, who's going to talk about a whole different application of min-max optimization now in the context of causal inference. So Nathan, take it away.
Thanks, Kostis, and thanks so much for having me. I'm sorry I can't be there in person. I have some childcare responsibilities here at home, but I'm hoping to be there later this semester. So I thought I would tell you about work that's joint with my student, Andrew, on the variational method of moments, which is essentially going to be about applying minimax optimization to solving conditional moment problems. So for motivation, let me start with the IV problem. So here, what I did is I took this orange curve and I generated data from it by picking some points X and then generating an observation by looking at the orange point with some noise. In particular, you can think about this maybe as some dosage of sulfonylurea, which is something that's supposed to increase the secretion of insulin in the blood, and then the insulin level. So we expect a positive relationship. But the way I generated this data actually is trying to kind of simulate something that might occur in reality, where maybe patients with the more severe disease are given higher doses. Right? So really, we're trying to capture a sort of constant insulin level. There's an insulin target that we're trying to get at. And indeed, if we look at the correlations between sulfonylurea dosage and insulin levels, it looks roughly flat if we just estimate that conditional expectation, but that doesn't reflect the actual causal effect, which is here in orange. And that's because what I did was I exactly planted endogeneity in this problem so that individuals with worse off disease were also given higher doses. So this is a problem called endogeneity. And one way to solve it is what's known as an IV, is to look for some source of randomization, here's Z, which is only influencing the outcome Y, here the insulin level, via its effect on X, the action, or other endogenous variables, here levels of sulfonylurea. So the IV model looks something like this. We have some sort of structural generative causal model that is saying, this is how X actually gives us Y. There's some function, theta naught, that takes X and gives us Y plus some noise. But because of endogeneity, actually the expectation of the noise given the variables is not equal to 0. This is the math of what the words endogeneity mean. And therefore, if we look at the predictive model of actually looking at the regression of Y given X, that predictive model is going to be distinct from this structural generative causal model that we want. So we don't just want to do regression, right? So IV is this tool that is very common in applications like econometrics that has some special properties that's essentially capturing the fact that it's giving us some sort of natural randomization in order to capture some sort of quasi-experiment that's hidden in the data. So one of the conditions it has to satisfy is exclusion. So in some sense, it should only affect Y via X, which we write by saying that it should be in some sense uncorrelated with the noise epsilon. So its only effect is via X. Okay, so we say expectation epsilon given Z equals 0, and it should also affect X in some sufficient manner so that it captures all the variations in X, at least in as much as they matter for the functions that we're trying to fit. Okay, and if we have these conditions, then we have that theta naught, this theta naught, the one that we really want, actually uniquely solve this moment equation over all thetas in our class of thetas, right? And this class of theta had to match the one for the relevance. In particular, it should be the case that if we look at the residuals, once we subtract from Y our causal prediction of it, theta X, those residuals should be mean independent of Z. So the means of the residuals given Z should be equal to 0. This is coming directly from the exclusion, and the uniqueness is coming from the relevance. So this very general type of model is sort of a workhorse of empirical research in econ. There's so many examples of different cases of trying to understand, for example, how veteran status affects earning by trying to understand the draft lottery number as a natural experiment. Or another famous one that recently won a Nobel Prize for David Card is understanding the effect of years of schooling on earnings. But of course, those things are endogenous via some sort of underlying skill or parentage. So using proximity to college as an instrument. And going beyond IV, essentially what we're dealing with here is a conditional moment problem that is something that shows up in a lot of settings beyond just IV regression. So the conditional moment problem is the following problem. So in IV, we had theta naught solves this conditional moment. It's a conditional moment because there's a conditioning on Z here. Now we're going to say more generally, we're going to observe some observations O. This is our random variable. And we're going to have some function that's known to us, rho, that takes O and theta. And we're going to say theta naught is the one that uniquely solves this moment equation, which is now in M dimensions. So before we had just one dimension, but generally would have M moment conditions. Okay, and what we observe is these observations O, and Z is just some aspect of O, it's some O measurable variable, and we want to learn, estimate, make inferences on theta naught. All right, so what are some examples of this? We only talked about one example, and that's instrumental variables. In this case, the observations consisted of the instrument, right? So the natural source of randomness that affects X and then only affects Y via X. And that was our observations, right? And here Z is O measurable because it's just that first element of O. And we only had one moment because we're looking at a univariate outcome. But there's a lot of other examples, not just IV. For example, there's the BLP model in industrial organization. It's essentially a just more complicated IV model with some discrete choice built in that helps us understand market shares. But beyond econometrics, this model is actually used to model Q functions and marginal density ratios in offline RL. So this is exactly those primal, dual, minimax algorithms that Jason was mentioning. It can also tell us some stuff about actually doing offline policy learning when we have circuit losses. I may get the time to talk about that as well. It shows up when we talk about proximal causal inference. So doing causal inference under when we have unmeasured confounders, but instead we can use negative controls to control for the confounders. It also shows up in panel data with confounders. And this paper is actually interesting. In this paper, what we had to deal with is actually, this is an example where theta naught might not actually be unique. So for the rest of this talk, I'm just going to focus on, let's just assume it's unique and deal with that. But sometimes it's not, and you have to think about how to target some sort of minimal such function. And the examples are endless. Now, the question is, how do you actually solve this problem? Right? So you want to find the theta naught such that when you project rho O theta on Z, that random variable is a zero random variable. How do we do that? So the first thing we might try is to reduce this to an easier problem, the marginal moment problem. So here, what we're going to do is we're going to fix some test functions, fj, which map Z to Rm. Okay, and then we can stack them all together. So we're going to take k of these, stack them all together into a matrix valued function. Okay, it's going to be k by m. And then we're going to form the k moments that we get when we multiply rho by f. Because the conditional expectation was 0, so should the correlation of rho with any function of Z be 0. Right? So we can test this with these k different functions. Right? There's a missing transpose right here. So that is essentially just the vector of length k, where in the jth entry we have fj of z transpose rho. Okay, so those k marginal moments should be equal to 0. And that is one way to try and find theta naught. Because we know theta naught at least satisfies these things. Okay, so we reduced it to the marginal moment problem, but how do we solve the marginal moment problem? Well, there's some very famous work about this, known as the generalized method of moments. So this is by Hansen. It essentially, one of the big reasons he won the Nobel Prize. And the approach goes like this. We're going to take these k moments, right? We have these k marginal moments, so we want to set all of them to 0. We want to find the theta naught that sets all of them to 0. we can't compute the moments exactly. Instead, we're going to compute the empirical version of the moments, right? So it's replacing expectations with empirical expectations. Whenever I write E sub n, I'm talking about this empirical average over the data. So now we have k empirical moments. We want to minimize all of them. We want to make all of them 0, okay? But we can't control all of them at the same time. So we're going to minimize some 2 norm of them. But the 2 norm is going to be weighted by some special weighting matrix, which is given by this formula here. Okay, so we're going to essentially try and control the 2 norm of this empirical moment vector. And the 2 norm is going to be controlled by this matrix, which is given by some initial estimate of theta tilde, which is essentially trying to give us an understanding of the covariance of these moment conditions. And why is the optimally weighted GMM, as I'm going to call it, so good? Well, one benefit is that it's consistent and it's asymptotically normal if theta naught is indeed the one that uniquely solves this, right? These k moment marginal moments. So if it's really you have a marginal moment problem, then that's great. This is what you should do. It's consistent, asymptotically normal, means we could do inference. It's even going to be semi-parametrically efficient in the model given by all distributions that satisfy these moment conditions, okay? As long as our initial estimate is consistent, which we can always do by just running GMM, plugging GMM into optimally weighted GMM, and be able to ensure this. So that's great. It gives us everything we want: consistency, asymptotic normality, and efficiency. But it has a lot of limitations. One is this assumption that theta naught uniquely solves this is pretty big. We were already not sure if it solves the, really solves the conditional moment problem uniquely. Right? In other words, it might not identify theta naught. It's not unique, right? And that pretty much shows up in anything that isn't linear IV. So if you have linear IV, right? So you have instrument of variable regression where that theta naught is a linear function, then you know how to identify it. But anything else pretty much is not going to work. It's not enough to solve the conditional moment problem. In addition, even if you're in that identifying case, like linear IV, it's not going to be efficient in the full conditional moment model. It's only efficient in this submodel, right? So that's actually almost anything that isn't both linear IV with a linear first stage regression. So pretty much anything. Okay, so what should we do? We should try and tackle more than just a few functions. Okay, so that brings rise to some approaches that have been suggested called Sieve approaches to this. So we can take optimally weighted GMM and combine it with some sort of Sieve, like a growing set of test functions. So this was back in the 87 done by Chamberlain, and more recently refined quite a lot and extended to other settings by I and Chen. So here we're just going to let the test functions form the first kn elements of some basis for L2 and let kn go to infinity, like permit polynomials, Fourier bases, B-splines, etc. So that's one thing we could do. We could also directly estimate the efficient instrument. There is actually a set of M test functions that are sufficient. They give us efficiency. They're just unknown. They involve some complicated conditional expectation. So Nui said, we know what these are in theory. Let's try and form them. And then we're going to estimate, this regression function, matrix valued regression function using non-parametric regression using sieves. Same thing with this vector valued regression, and actually plug in F star into optimally weighted GMM. So the good thing is that these are efficient under appropriate conditions. The bad thing is that these are kind of unusable in practice when theta and z are just moderately dimensional. Right? We look at this regression. If we have theta being moderately dimensional, the size of this vector could be big. If z is high dimensional or just moderately dimensional, this non-parametric regression is going to be really, really hard to do. Right? What we want to do is not use all this classical non-parametric statistics that's not so useful in moderate dimensions. We want to use something more machine learning like. So that has recently given rise to these minimax approaches for this problem. So the minimax approach would go something like this. Instead of just fixing k test functions, we're going to look at a rich class of test functions, right? A big class of functions from input space z to r to the n. Remember, m is the number of moments that we're trying to set to 0, right? It's the number of conditional moments. For example, this set could be neural nets with m outputs, product of RKHSs, et cetera, et cetera. And then what we're going to do is we're going to look for theta that would minimize all of these moments for all of these f's in this class of functions, right? So we're trying to find theta that would make many, 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 many moments equal to 0 in a big, rich class of functions, right? So we can not just use k moments, just k test functions, we can use a whole RKHS, a whole neural net. And that's something that's been proposed in a variety of recent work and actually shown to work quite well in a lot of those applications like offline RL, IV regression, etc. But there are limitations to this as well. So first, on the positives, the benefits are that identification is now much more plausible. As long as F is sort of going to be dense in L2, we're done. This is exactly the same thing as the conditional moment problem, right? We haven't made any sort of assumption that we found k-sufficient things to identify. There's no longer crazy sieves, no Hermite polynomials and unwieldy stuff like that, no splines. It's much more ML-like, right? Put a neural net in it, maybe you grow the neural net. Put an RKHS in it, stuff like that. And this, in particular, this paper that I want to point out in particular gives us rates for how fast we learn theta naught when we think about non-parametric classes for theta and for F. And I believe Vasilis will tell us about this later this week. But there's also some limitations here. First of all, efficiency, right? So you can get consistency, you can get rates, but even if you get square root n rates, what's the constant in front, right? Are we doing this efficiently? Even when we talked about that classic marginal moment problem, you can easily get square root n consistency without doing any special weighting. But the efficiency, that Nobel Prize winning efficiency came from optimal weighting. Right? And the problem here is there's a lot of moments, right? There's infinitely many moments, and we don't know which moment should weight more or less. There's going to be a lot of duplicate moments that kind of are correlated, and we really have to worry about to control the right moments that matter and not control the moments that don't matter. Don't waste your time trying to make theta control the moments that actually don't matter so much, right? And that's going to matter a lot in practice. And actually will be important for actually getting semiparametric efficiency. In addition, while we're able to get these rates for non-parametric theta, the question is, but what about inference? We want something like asymptotic normality so we can do plus minus 2 standard errors, because maybe what we're trying to do here is we're trying to do, economics, we're trying to do social science. We want to make claims about things that are out there in the real world. We want to put confidence intervals on things and make claims that are true. We want to do inference. Right? So that's kind of a big deal. So what I'm going to try and do in today's talk is try to tackle how do we get these two, efficiency and inference, within the context of minimax approaches to the conditional moment problem. So that's going to be what I'm going to set out to do. And that's going to lead me exactly directly to the method, the variational method of moments that I'm going to propose, which is going to try and tackle those things. So my plan is going to be present this methodology, then show you the guarantees for this methodology. We're going to go through consistency, asymptotic normality, and semiparametric efficiency. So all the things that we want. And then we're also going to talk about how to actually do inference with this. So it's going to be asymptotically normal, but we also have to estimate the asymptotic variance so that we know how to do plus minus 2 standard errors. Like, what are those standard errors? So we'll talk about, again, a minimax on top of minimax algorithm that's going to give us the inference. I'll talk a little bit about experiments. And if there's time, we'll see where we get. I literally just put these slides together, so I just put extra stuff there in case there's lots of time. But it's not about what you cover, it's about what you uncover. So we'll see where we get. If there's time, I'll talk about applying this VMM methodology for policy learning and applying this VMM methodology for off-policy evaluation when you see confounded observations from a POM-DP. So a sort of confounded version of offline reinforcement learning. But for now, let's just talk about the variational method of moments. So before going to the variational method of moments, let's go back and talk about optimally weighted GMM. What I'm going to try and do is I'm going to start with optimally weighted GMM, and from there, go to a minimax formulation of it, so that we can then generalize for rich function classes. Right? We want to inherit this efficient optimal weighting that Hansen gave us. Okay, so toward that end, let's recall what optimally weighted GMM was. It said, let's take k test functions, and we're going to pick theta at hat n to minimize the vector norm of these k moments, right, empirical moments, weighted by some appropriate matrix. It's going to give us the right Euclidean norm to minimize, right? It's going to weight the moments in the appropriate way so that we get efficiency. So you can actually just rewrite this Euclidean norm using duality as a soup. So it goes something like this. If we fix f to be the linear space of functions, right? So linear space of functions from z to r to the m, which is given by the span of these kf's, right? Literally, for any combination, any betas, we're gonna, there should be no transpose beta here, that's a typo. We're gonna look at mapping z to some linear combinations of fj. Okay? Then we can show that this optimally weighted GMM is equivalent to the following. You're gonna minimize over theta, the supremum over all functions f in the span. Okay, so now this is calling to mind the minimax approaches from before, but this is not any different from optimally weighted GMM. This is optimally weighted GMM. So we're looking at the supremum over all test functions f in this span of the empirical moment that this test function gives us, minus some regularization that accounts for the variance of this. Okay, and this will actually be 1-to-1 equal to the above, just by Euclidean norm duality. But now this is very, very suggestive. Now that we have a soup f over f, we can say, let's just switch out f by other function classes and just hope that we've inherited the nice properties of optimally weighted GMM. Okay, that's going to be the plan of attack. So just let's define VMM here first specifically. So VMM is going to be given by a choice of function class Fn, a choice of some initial guess for theta, not theta tilde n. Usually we're just going to be using the previous iterate. So we're going to try first, get an estimate, plug it in, get a new estimate. 2 rounds will be enough, but we can proceed more rounds if we want to. And some regularizer for f. Okay, so let's work through these terms. What is going on here? What are we trying to do? This purple term over here is trying to make all the moments 0. This was the same motivation as in the minimax approaches. We have a lot of test functions. We want to make sure that the moments with respect to each test function is made very, very small. So that's the first term. But we need to know what is the kind of the relative importance of different moments. That's the second term. It's telling us, make certain moments with certain test functions less important or more important accordingly to their variance. Finally, we're going to control the complexity of our function class by either changing the set of functions we're looking at and or choosing a regularizer. There's some sort of redundancy there, but because of the flexibility this allows us, I'm going to include both a possibility for choosing growing function classes and having some regularizer. Okay, so that's the VMM, right? Now I'm saying we're going to minimize this, but we can actually also permit some approximate optimization. We can have that theta n is only approximately optimizing the supremum, which will be useful in practice and is not going to change any of the results. But to keep things simple and straightforward, we're just going to stick to exact optimization for now. Okay, so as I alluded to, we can also, right, the question is where did theta tilde come from? Well, it goes like this. You can just apply VMM on top of VMM. So you initialize some guess for the parameters, maybe just all zeros, whatever you want. And then you're just going to use that previous iterate as your current guess theta tilde in order to control this orange term. And then you're going to find your next guess for theta hat n. And then you can keep doing this k times. You only really need to do this 2 times, but you can do this multiple times if you wanted to. Okay, so this is kind of a generic recipe. Let's talk about specific variants of KMM, of VMM. So one variant would be to instantiate everything with kernels. Right? So let's say that H is going to be some reproducing kernel Hilbert space or ArcHS, for example, Gaussian kernel, product of M Sobolev spaces, whatever we want. We're going to set Fn to be this ArcHS. And we're independent of n, and we're going to set the regularizer to be given by the squared Hilbert norm of the function f. Okay, so that's one variant of VMM. This is the variant that we're actually going to focus on in the theory. But another variant we could do is use neural nets to instantialize everything. So we're going to set Fn, the class of functions, to be a class of neural networks with some given architecture and unknown weights, and the architecture could be growing, right? So later we're going to talk about a fully connected neural net that has growing width and growing depth. Okay, and there's different regularizers we can choose. So one regularizer I'll talk about is the kernel regularizer. So essentially use the same regularizer as from the kernel VMM. These functions, right, these neural nets are not actually in the RKHS. So instead you're going to look at the function that interpolates the neural net at every data point, right? It's going to exist if we're going to look at universal RKHS like this and look at its norm, right? So the norm of the minimal interpolating element of the RKHS and use that as a regularizer. This looks a bit complicated. It has some infinite, but it has some closed form. It's some quadratic in the evaluations of f and zi. We could also just regularize the squares of the values that f takes on zi. And that's going to approximate essentially doing this kernel regularizer with a Gaussian kernel with very tiny length scale. So this is sort of heuristic practical version of this, which is what we're going to implement in practice in the experiments. But this kernel regularizer is what we're going to study. Okay, so before I talk about guarantees, let me talk really quickly about how we actually compute this. Right, so VMM here is given by smooth games. I guess that's why I'm here today telling you about it. It's a game between theta and the test functions f, optimizing some potential. Right, so how do we solve it? I don't know. I guess the people in the room are way better equipped to tell me how to do it. I'll tell you how I've done it in the experiments. You probably know how to do it better. Right, so for kernel VMM, the inner soup actually has some closed form. We can write it as a convex quadratic in the values that the moment function rho takes, right? So it's going to be some convex quadratic in these, and then we're going to optimize over theta. It's going to be in terms of some of the kernel gram matrix and the value of the moments at this initial guess theta tilde. Okay, and then we can directly apply usual optimization algorithms to this because there's no soup anymore. We solved the closed form. For neural nets, it gets a bit more complicated. And there in the experiments, I used OWGMM, which is, this paper from Kostis and Vasilis and someone else, I'm forgetting, I apologize, from 2017, which is talking about how to optimize these smooth games. And it works great for us here. There's been a lot of development since. So I'm sure there's a lot of opportunities to potentially improve. Actually, interesting story. I was 2018. We were doing this work. We were trying to figure out how to do it. We had a lot of the theory figured out, not for this inference stuff, but for earlier things. But the experiments were just terrible. We couldn't optimize it, right? It seems like in GANs, you can kind of get away with the ascent-descent, but it was just not working for us. And I was in NeurIPS 2018, and I saw that Kostis was running the smooth game optimization workshop. And I thought maybe I'll go learn something. And that's where I learned about this. I asked Kostis how to do it, and he said, oh, you should use this. And it was magic. It just worked. And then we were able to complete this. So that's a story for actually implementing this, optimizing this thing. But let me tell you about something that is kind of more special or maybe a bit newer and beyond just smooth game optimization, which is what are the statistical guarantees that we can give about this approach? Okay, so let me start with consistency. And of course, we're going to need some regularity. Okay. So we need some pretty kind of mild regularity. That's not saying too much. We're not making too sort of complexity assumptions. The only complexity assumption we're making is about theta. Theta needs to have a finite entropy integral. This is trivial if theta is a finite dimensional parameter set, right? And this is going to be trivial. Otherwise, we're just going to assume that these moment functions are equi-Lipschitz, they're bounded. We're going to assume that our initial guess, theta tilde, converges to some fixed theta tilde, has some fixed point. And in particular, also the rows evaluated at theta tilde n converge to theta tilde. And both of these things will come for free when we do k-stage VMM. But for now, I'm just going to make this as an assumption about theta tilde n. And we also need, nice second moments to the moments conditions. And under these assumptions, and absolutely no other assumptions, we can show consistency. So let H be any smooth universal kernel, like Gaussian. Set alpha to be something that's between 1 and 1 over root n. For later, we're going to have p equals to 1/2. So just anything, the regularization should be anything between 1 and 1 over root n. And then kernel VMM with this function class is going to be consistent. That's it. It's going to converge to theta naught. We didn't make any functional assumptions about kind of complexity in Z. That was actually not important. Although it was important, was complexity of theta, because only theta is what we're trying to estimate. Now, we get this for kernel VMM. And sort of as a corollary, most of the work is about kernel VMM, but we can always play this trick of having a set of neural nets that is sufficiently big so it approximates things sufficiently nicely, sort of kind of just has to approximate these Sobolev spaces. So by playing those tricks, we can show that the same is going to be true if you're going to use a neural net VMM with a fully connected neural net that has a width and a depth that are at least some certain amount that we give in the paper. If it's even bigger, that's fine. There's no problem if it's even bigger. Right? The bigger, the better. We just have some minimum sizes that are necessary, and then use the kernel regularizer given by H. It's essentially trying to mimic this kernel VMM, and therefore it inherits this result. Okay, but consistency was not what we came here for. So let's talk about asymptotic normality. So now I'm going to switch to talking about asymptotic normality and about efficiency. I'm going to focus on finite dimensional parameters. So theta is going to be b-dimensional. In this case, the covering assumption is going to hold trivially. I'm going to need some additional assumptions. I'm going to need sort of smoothness of rho, but only second moments, not like d over 2 derivatives sort of kind of thing that says things are downscript, just second derivatives. And I'm going to need sufficient support so the variances are not crazy. So these functions, as functions of z, should be linearly independent functions. And under these additional assumptions, again, no complexity assumptions on the conditional moment function, right, the function of z, we can show that if we, again, use H as some smooth universal kernel RKHS, like Gaussian, and if we choose alpha to be something between 1 and 1 over root n, then the kernel VMM is both going to be asymptotically linear. So asymptotically linear says what? Asymptotically linear says our estimate looks roughly like a sample average of some function, some unknown function psi. This is called the influence function, plus some low order noise. So mostly it looks like a sample average. In particular, our estimate is going to be asymptotically normal. Right? So if you look at the scaled error, theta hat n minus theta naught, scaled by square root n, that's going to converge to normal with mean 0 and some variance, with some complicated expression in the paper that also depends on the limit point theta tilde. Again, neural VMM inherits this by just playing this trick of having really, really large neural nets that approximate everything. Okay, so we got normality. We almost got inference. We just have to kind of get this v theta tilde and we're done. We can get more than that. We can get semi-parametric efficiency. So in particular, we can show that that variance from the last slide, when theta hat tilde, theta tilde n converges with theta naught, right? So the asymptotic covariance of VMM, when our initial guess converges eventually to theta naught, as it will if we do two-stage VMM, that is actually the semi-parametric efficiency bound for estimating theta naught in the model consisting of all distributions satisfying the conditional moments. Okay, so it's kind of like what Hansen got for the marginal moment model, but now we're looking at the model specified by the conditional moment problem. Right, so this is in fact the semi-parametric efficiency bound, and therefore these k-stage kernel or neural VMMs are going to be semi-parametrically efficient in the conditional moment problem. So just a quick recap. What are we talking about? What is the semi-parametrically efficient? Essentially what we're saying is that if you look for any beta at the asymptotic mean squared error of estimating beta transpose theta naught, right? So some aspect of theta naught, some contrast, some univariate aspect of theta naught that you care about, right? We're going to achieve the minimum possible asymptotic mean squared error. Right? So minimum possible, either literally minimum possible among all regular estimators in this model, or we can also think about it as among all estimators in some locally minimax sense. Okay, so this is sort of classic semi-parametric efficiency theory. So we checked all the boxes. We got everything we want except inference. So what does inference mean here? Inference means estimate that, right? Estimate this covariance. Once you estimate that covariance, then we know how to construct confidence intervals. It's asymptotically normal. With this covariance, you can just do plus minus 2 standard errors or any sort of test like that. Okay, so how do we estimate that? So we could literally estimate it by, again, going back to NUI and kind of doing non-parametric regressions and figuring it out. That would be some consistent way, and really only consistency for the covariance in order to get valid confidence intervals. But there's actually a nice way to layer VMM on top of this to estimate this. So we can show that if V theta naught is this efficiency bound, and you care about some aspect of it, right? So some quadratic form in it, right? Why do we care about this thing? Because this is going to be the asymptotic variance of beta transpose theta hat naught. That is going to be given by its own smooth game, right? Again, we're going to look at a game between this B-dimensional gamma and F, but now it's sup inf instead of inf sup. So all we're going to do is we're going to take this characterization of the efficiency bound, and we're going to replace expectations with empirical expectations and add a regularizer because we can. Okay, and then that's going to be our VMM style estimate of this variance. And we can show that under these sort of same conditions that we had before, kernel VMM standard error estimates is going to be consistent, right? This way of estimating the standard error is really going to converge to the true standard error that we care about. So in particular, if we have some aspect psi of theta naught that we care about, we can construct a confidence interval just by taking psi of the VMM estimate plus minus 2 of these guys when we plug in the gradient of psi for beta, right? That is going to be exact 95% coverage. And we have a way of optimizing it, I guess, again, using the kernel gram matrices for the kernel case. So all good. So now in the time that's left, I'm going to try and walk through some of the experiments of actually trying to apply this in practice and seeing what are the benefits of using this. What are the benefits in terms of mean squared error? We said, I said that we should get minimum mean squared error. Well, asymptotically, how does that bear out in practice? And, how does the inference work? This is sort of the first inference method for these minimax methods. Does it give us what we want? So first, rather than tell you about the setup of the experiment, there's no point to it. I'll tell you, we look at first a simple setting and then a more complicated setting. And at a high level, the story is as following. If you're interested in kind of the specifics of the setup of the experiment, you look in the paper. But here I'm just looking at different estimators, the VMM estimator, these Sieve estimators, various Sieve estimators, as recommended in the Ian Chen paper with different versions of that. These sort of maximum mean restriction methods, and a naive method that's just doing plain regression, no control for the IV. And in this sort of simple setting, kind of everything works. Everything is getting reasonable MSE, and it's essentially just showing everything works as it should. And for example, VMM is not exploding. When we go to a slightly more complex scenario, that's where we see things play out. These Sieve methods they're just insane, right? The Hermite polynomials, it's actually here we used B-splines. It's just completely unwieldy in practice. And the MSE is just not even, I can't even write it down in this table without it fitting in the slide. The VMM methods seem to perform reasonably well, better than just using this maximum moment things. Okay, so maybe we can attribute that to efficiency, right? That we're actually getting the best possible asymptotic MSE. Right? So hopefully our MSE should be smaller. And it seems to bear out in practice here. We can also talk about not just the MSE of the thetas, but what is the L2 error of predicting, right? Predict the actual insulin level average over, average of scared errors over the insulin levels. And we see, much better performance as n grows than especially the Sieve method, but also the maximum moment method. So for inference, inference is hard. We get about the right kind of coverage. Definitely for small n, we're undercovering a lot. For slightly bigger n, we're getting more nominal coverage, close to this 95% coverage. But it's definitely, if you also look at how well we're estimating standard error, we're getting it about right. Okay, so that's even when we use sort of these very complex function classes. Now, here I was focusing a lot about finite dimensional theta, right? So we actually proved consistency for general theta, non-parametric theta. We just needed the theta class to be Donsker. But efficiency in inference only makes sense if we have a finite dimensional theta, right? Because we're talking about efficiency bound, we need some finite dimensional parameter to talk about. We're talking about asymptotic normality, we need to talk about some finite dimensional theta. So what about general non-parametric theta, right? So this recent paper by Dikal et al., that Vasilis, I think, is going to tell us about later this week, provided some really nice non-parametric finite sample guarantees, right? So they take this unweighted minimax method, and they show that under, in terms of kind of the non-parametric complexity of big theta and of script f, they provide finite sample guarantees. But we know that these plain minimax methods are not efficient. Okay, so we get the right rates maybe, but we need maybe waiting to get efficiency. But efficiency is not a story about rates. It's a story about the leading constant on first order terms. It's hard to explain kind of what's the effect of optimal weighting in terms of finite sample guarantees. It would essentially be the leading constants, but it's actually hard to characterize in this case when we're talking about these non-parametric cases. Maybe, you know, I'm thinking about this. I haven't been able to figure this out, but it does seem that in practice, even when we're not talking about finite dimensional theta, adding this regularization does help us even when we're doing non-parametric estimation. So just to give you a sense of this, here I'm looking at trying to estimate different functions, so either a sine, a step function, or absolute function, or linear function, but the noise is going to be confounded with the x. Right? So even though I should be fitting a step function here, if I look at the data, it just looks like a line going up, right? And if I actually estimate this with neural net regression, that's what I see. But really, I should be using the instrument, which is not shown on the slide, but I'm also giving some instrument that is able to tease out what is the structural causal generative model here. And here I'm looking at a variety of methods that are trying to now learn this IV regression in a non-parametric way. They're not just trying to find finite dimensional theta, they're actually trying to fit some deep neural nets, some rich IV regression, right? So in these different settings, we can look at what happens when we just try to regress directly, or what happens when we try to do things based on sort of linear IV with some sort of basis expansion, and that works when the basis expansion is right? Either it's linear, when it's like quadratic-like, it seems to work okay, but you know, doesn't work for step. And here are different approaches that you could apply. You could either literally do GMM on the neural nets, or you could do this sort of minimax methods, or you could do sort of two-stage methods, and they seem to improve. But they also have some failing points. And it seems that adding this regularization and trying to control which moments you're optimizing and which moments you're spending expressive energy on can really help you in practice, right? But this is outside the scope of the semiparametric efficiency results. This is just something I've observed empirically. I think I'm out of time. So rather than talking about these applications, right? So here I have some more results. These are actually other papers. This paper is from NeurIPS. This is another recent paper where we look at how to use this for confounded POMDPs. So rather than tell you about this, I'll just recap here and tell you the punchline. Here, okay, we do better. Of course, that's what the experiments are going to show. Okay, so I'll go to the conclusion. So we saw that these conditional moment models are extremely useful for a lot of problems. It's a workhorse of economics, right? All these IV or industrial organization have some sort of conditional moment problem underlying them. But it's not just in economics. It's also really important in offline RL. I mean, Jason showed us that all those primal, dual, minimax estimators for Q functions, for density ratios, they're coming from conditional moment models. And it's also especially important when we're looking at confounded settings where we actually can only use conditional moment models. You can't use sort of repeated regression, sort of DP, like FQI is essentially a DP method, dynamic programming with a regression. So in these confounded settings, you really can't do regression. You really have to think about this as a conditional moment model. It's more like the IV version of offline RL. And, you know, I didn't get to talk about this, but you can actually also do this for cost-sensitive classification. I'll just mention a quick insight from that setting, which is if you're looking at cost-sensitive logistic regression, logistic regression is actually not optimal there. Even though Emily says that, you know, if you're actually fitting something in the case where something is really a logistic response, it's optimal. It's not optimal in the cost-sensitive setting, and you really have to do something more clever to get efficiency. Right, so Sieves is sort of the classic approach to this. You know, it's been developed in the past millennium, and it was shown to have nice properties, but it doesn't work in practice. It's just completely unwieldy. So that's recently led people to look at these more MLish Minimax approaches, but they lose the noble winning efficiency and inference of these classic methods. So what I try to do is try to go back to optimally weighted GMM and try to directly translate that to this Minimax setting with general function classes more directly in order to keep that optimal weighting. And we showed that that gave us asymptotic anomaly, semiparametric efficiency, and a way to estimate standard errors. And it seems to work well in practice, even beyond finite dimensional theta, but I can't say anything about that theoretically. I would love to hear if you guys have thoughts about what to do there. Thanks.
Thank you, Nathan. Are there any questions for Nathan? Also, Nathan, if you can see your chat over there, in case there are questions from the online participants, please monitor that. Otherwise, I'll monitor the questions in the room.
Okay.
Yeah.
Hi, Nathan. So I was wondering if there is any trade-off between the statistical efficiency versus the computational efficiency, because you mentioned you can use these fully connected neural networks, but the resulting Minimax problem is going to be non-convex, right? Non-concave, then it is very hard to solve it.
Yeah.
Yeah.
I haven't thought about this a lot, honestly. I was mostly concerned with the statistical properties, and I hoped that, you know, smarter people like Kostas figured out how to do the optimization. So I don't know anything theoretically about this, right? What I do know is for the kernel version, right? Even for the kernel version, the inner supremum is closed form, but it's still some crazy optimization problem. For example, if you're optimizing for neural networks data, like you're doing neural net regression. So I think that's a good question. I don't know how to study the computational complexity because it's just always going to be some weirdo thing. It's never going to be convex, poly time solvable. At least it's not so clear to me. Do you have some thoughts on this?
I think most of us here are still trying to figure it out, right? But yeah, thank you.
Thank you.
Listen, thanks for the talk. One question is like, one way to maybe equalize the variance of the moments would be to just standardize the moments, divide by the variance, and optimize that objective, like a minimax objective where every moment is divided by its variance. Do you know how that would compare?
So you're saying instead of doing -1/4, do this?
Yeah, standardize every moment by dividing by its.
Would it be what you're saying? Is
yeah.
Purple divided by orange.
Yeah, something like that. Yeah.
Okay. So arg min soup purple divided by orange.
Yes.
I think on the right way that should be equivalent. I think.
Okay.
That's a good question. Sorry, I don't have but I'll think about it. That's a really, really great question.
So I have a question maybe related to this. I'm a little bit confused. So if this theta and tilde is a bad initial estimate, what is going to break? Like your confidence intervals are too big. So what is...
What will break is the following. So imagine first that it's so bad, right, that maybe let's say rho of when theta is equal to 0, rho of it is 0, right? So if we start at 0, this will be completely eliminated, right? So we'll only have this minimax thing that we had before. So what this tells you is how should you weight the different moments? So that came directly from optimally weighted GMM, where gamma hat here, it should have been what you really wanted was you wanted the covariance of these moment conditions, but you didn't know at theta naught, but you didn't know theta naught, so you did it at theta tilde, right? So you could look at putting an identity matrix here and saying, you know, let's just look at the 2 norm. Once you've done that, you've got an initial guess for theta hat, and then you can try and get a better guess for gamma hat. So what happens if you, like, look what happens with this. If I put the identity here, right? So I don't weight things correctly, and I have duplicates of the moments. So maybe I have F1 and F2 are equal to one another, and then there's F3, which is another one. I really should somehow equally weight F1 and F3 and forget about F2, but I'm doubling up on F1, F2 by saying I care about twice the squared moment for F1 and once the squared moment for F3. Really, because those F1 and F2 are perfectly correlated because they're the same function, they're the same F, I should discount that. That's exactly what this gamma inverse does, right? So that's what it does in optimally weighted GMM. It makes sure that I'm eliminating sort of these duplicate moments. And it's exactly what it's doing here, because the way that this plays out in order to show this thing for kernel VMM is doing a sort of argument like this, where everything is now like these operators on RKHSs rather than matrices. And you need a lot of regularity, and you need to do regularization because these are universal, etc. But if you get a wrong theta tilde, it means you don't know how to correctly re-weight things. Now, you might think, why don't I just stick theta itself here? I don't know, I have a very good explanation for why that's bad. I think, you know, it's kind of related to maybe, I hope this is, yeah, kind of like this double sampling in offline RL. Yeah, sorry, did that answer your question, Kostis? So you care about...
Yeah, I guess I was asking more what, like, where in your theorem is reflected that, you know, if theta and tilde is, you know, a bad choice, something will break.
Yeah.
Like
So,
in this there was some...
yeah.
So, okay, so it will affect your variance. That I guess that was my question.
Will depend on the p limit of theta tilde n, which is assumed to be exist and to be equal to theta tilde. So there's some thing like this, and the PSD smallest value that this matrix can take is at theta naught. That is going to be PSD preceding v theta tilde for any theta tilde. V theta naught is going to be PSD smallest, respected like the PSD ordering.
Okay, yeah, so that, I guess that was my question. Yeah, and then okay. So in practice, you hope that I mean, if you do 2-step of your VMM framework, you hope that you'll get some reasonable theta tilde there. Is that the hope?
Oh, you don't just have to hope. I mean, that was the consistency, right? So consistency told me that kernel VMM with any theta tilde, just like whatever, it doesn't matter, just put zeros in there, will be consistent. Therefore, I can plug this theorem into this theorem to say that if my theta tilde n is doing kernel VMM first with some bad theta tilde n, then I'm golden. Then it's fine,
Gotcha.
right? And that's what I try to summarize here. That k-stage VMM with at least 2 stages will be semi-parametrically efficient.
Yeah, okay, that makes sense. Thank you.
Yeah, thanks for the question.
Arthur.
Hi, Nathan. Thanks for the talk. I just have a question about this kernel regularized fully connected neural nets versus just kernel methods. So I'm just wondering, like, given, I'm not sure I understood completely, but it seems that your kernel regularizer of your neural nets is sort of to make it behave more like a kernel method in your analysis.
Yeah.
If I read your table right, it seemed that it was doing a little bit worse. Is that correct in the more complicated models?
It's a bit of a wash. It's hard to say. I think like so in the simple setting, it seemed to do better. In the more complex setting, you're right, it seemed to do a little worse.
Right.
I'm not sure what to read of it. I mean, I think here my regularization is actually not the kernel regularization. It's this Frobenius regularization, this cheat regularization that I didn't actually theoretically characterize. And I would hope that the neural nets would also have some inductive bias that should help. But yeah, it doesn't bear out in the theory. In the theory, it's just the neural VMM only works because it's mimicking the kernel VMM. But your point is like maybe it's actually worse because it's only mimicking it. Maybe. I'm not sure.
Right. Yeah, no, I mean, I'm just curious. So whether in practice there was a difference in the performance for different settings of the neural versus the kernel method. But perhaps in this case,
we have another scenario for the policy learning where the neural thing did better.
Okay, thanks.
And at least asymptotically, they should all behave the same.
Right. So if there are no more questions, let's thank Nathan again. Thank you, Nathan.
Thank you. So I'm wondering, can you just see my slides and hear an ominous voice in the room, or you also see me waving at you guys?
I can see you. Yeah.
Okay.
Bye-bye.
Thanks so much.
Thank you. Yeah, for those of you who are physically here, there's a reception outside.